Hello, I am Milad Gazdavi from the University of Waterloo. I present our paper, Fault-Tolerant Service Function Chaining, which assists them to make a chain of mailboxes fault-tolerant. This paper is a joint work with my colleagues Elahi Jalalpur, Bernard Wang, Rauf Boutaba, and Ali Mashtizadeh. Mailboxes are prevalent in enterprise networks providing different functionalities. Examples of mailboxes are firewalls, IDSs, and NATs. Packets commonly pass through an ordered sequence of mailboxes called a service function chain or simply a chain. Network operation depends on the reliability of mailboxes and service function chains. Because of their critical operation, mailbox failures are the largest source of high-severity network incidents reported in one data center study. Although mailboxes are only 11% of total network devices, they contribute to 43% of high-severity incidents. Their failures also have led to major service outages. As a result, there is significant work to build fault-tolerant mailboxes. The basic idea is to have a mailbox backup so that upon failure, traffic is redirected to this instance. In this example, upon the failure of the primary NAT, the traffic is redirected to the backup NAT, which resumes the NAT operation. Providing fault tolerance for mailboxes is challenging because the state must be replicated consistently. If the state becomes inconsistent, mailboxes can drop connections, route traffic to wrong destinations, or even cause outages. In this example, Alice's connection is dropped due to inconsistent replication. Previous approaches to mailbox fault tolerance fall into two categories: externalized state approaches, which separate the mailbox state from its logic and store it to a remote fault-tolerant data store. The second approach includes snapshot-based systems that take and replicate snapshots of mailbox state. Let's have a closer look to build a fault-tolerant mailbox, for example, a NAT using externalized state approach. NAT becomes stateless and its state is stored remotely in a fault-tolerant data store. When the NAT receives a packet, it might need to read the state remotely. It might also need to update the state, which requires sending a write request to the data store and waiting for the acknowledgement before releasing the packet. Accessing the state remotely significantly increases the packet latency. Let's see how snapshot-based approaches work. Snapshot-based approaches ensure consistency by taking and replicating consistent snapshots of a mailbox's state. In this example, when the NAT receives a packet, it holds the packet until a snapshot of the state is taken and replicated to the backup. The NAT waits until it receives an acknowledgement from the replica, then it releases the packet. To ensure consistency, NAT does not release any packet until this synchronized replication is completed. Some approaches take snapshots per packet. Others may take snapshots periodically. While taking the state snapshots, the mailbox operation stalls. Let's look at using snapshot-based approaches for a chain of mailboxes. In a chain, a snapshot-based approach must pay the cost of synchronous replications at each mailbox of the chain. Furthermore, taking periodic state snapshot at each mailbox causes operational delays that significantly affects the throughput, similar to a pipeline stall in a processor. While a mailbox takes snapshots, not only its operation pauses, but it essentially stalls the operation of preceding mailboxes. These results in high latency and low throughput. Using existing solution for a chain of mailboxes comes with significant performance overheads. This motivates us to explore another approach to provide fault tolerance for a chain of mailboxes. Instead of making individual mailboxes fault tolerant, we explore a different approach to replicate the state of the entire chain. For example, in this approach, the state of firewall, as shown, is replicated down in the chain by the IDS, and the state of the IDS is replicated by the NAT. The goals of our approach are to provide consistent state replication to tolerate F middle box failures, to minimize the overhead of providing fault tolerance during chain normal operation, and to minimize the disruption due to middle box failures. To meet these goals, we introduce a new system called fault tolerant chaining, or FTC. To make a chain fault tolerant, FTC uses in-chain replication to replicate the state of middle boxes across the chain. To tolerate F failure, this approach replicates the state of a middle box to subsequent F middle box servers. FTC also improves the performance of fault-tolerant multi-core middle boxes using transactional packet processing. Packet transactions also simplify the development of multi-threaded middle boxes. FTC also using data dependency vectors to correctly and efficiently replicate the state of multi-threaded middle boxes. Let's have a closer look on how FTC works during the normal operation to tolerate a single failure. For a chain of 3 middle boxes, for each middle box, FTC instantiates a replica. In addition to a state replication, a replica also provides a state management API to control the access of a middle box to its state. This is necessary in providing fault-tolerant state. These replicas are co-located in servers hosting the middle boxes. The dotted lines show physical machine boundaries. In addition, FTC adds 2 other components, a forwarder and a buffer. I will discuss their purposes later. FTC components communicates as shown. Let's see how FTC processes a packet to tolerate one middle box failure. When the forwarder receives a packet, the forwarder piggybacks some state to the packet and forwards it to the first replica. I will describe where this state comes from later. R1, the first replica in the chain, detaches and replicates the piggyback state and forwards the packet to the middle box to be processed. While the middle box is processing the packet, R1 tracks the state changes made by M1. And once the packet processing is complete, R1 piggybacks onto the packet the state changes and forwards the packet to R2. As the packet passes through the chain, replicas replicate the piggyback state updates. This allows each server hosting a middle box to act as a replica for its predecessor middle boxes. In this example, R2 replicates the state of first middle box. Once the packet is processed, R2 piggybacks state changes onto the packet and forwards it to the next replica. R3 performs the same set of operations and forwards the packet to the buffer. The state changes of M3 has not yet been replicated in enough number of replicas to tolerate one failure. We need to replicate its state in at least 2 replicas. For middle boxes at the end of the chain, FTC transfers and replicates their state updates in servers hosting middle boxes at the beginning of the chain. This allows FTC to eliminate the need of any dedicated replica servers to tolerate failures. FTC uses the buffer to withhold the packet until the state of middle boxes at the end of the chain, in this example M3, is replicated. The buffer strips and transmits the piggyback state to the forwarder. The state sent by the buffer is the state of the forwarder. The forwarder piggybacks the state of M3 onto an incoming packet and forwards this packet to pass through the chain. R1 is a replica of M3 and replicates the piggyback state of M3. Now the state changes of M3 have been replicated into replicas. This allows FTC to tolerate one middle box failure and recover the chain state up to the changes made by the blue packet. R1, in addition to state changes of M1, piggybacks some metadata to the packet, showing the latest state that it has replicated for M3. The packet passes through the chain. Once the buffer receives the packet, it analyzes the metadata of the piggyback state and realizes that M3 state changes due to the processing of the blue packet has been replicated in 2 replicas. Then the buffer releases the blue packet. Upon a middle box failure, FTC selects a server, instantiates a replica. This replica concurrently fetches the lost state of R2, including M1 and M2. Once the state is fetched, FTC instantiates M2. Then FTC routes the traffic towards and from this new middle box. To support concurrent packet processing, FTC introduces transactional packet processing. Most of existing solutions only support single-threaded and batched packet processing. FTMB, the state-of-the-art, is the only system that provides concurrent packet processing. However, FTMB uses complex design to track a state in granularity of any read and write on every state variable. FTC uses the concept of packet transactions for simpler design. The isolation property of transactions allows FTC to track state changes in granularity of each packet transaction. FTC also does not track read-only transactions. For details of transactional packet processing, please look at our paper. FTC uses data dependency vectors to provide concurrent state replication. Data dependency vectors are inspired by vector clock algorithm to ensure that multiple replica threads replicates the middle box state consistently. Vector clocks are conventionally used to track thread operations. The number of threads must be fixed. This thread-based approach requires the middle box and its replicas to use the same number of threads. In addition, there must be a one-to-one mapping between the middle box's threads and replicas' threads. Instead, FTC tracks data changes. Specifically, FTC divides the state into multiple partitions and uses a vector of sequence numbers to track the state partition changes. Data dependency vectors allow a middle box and its replicas to use different number of threads. In addition, data dependency vectors allow vertical scaling. As shown in the table, middle boxes are provided in different flavors, providing variety of throughput capacities with different CPU core demands. Using data dependency vectors, a middle box can fail over to a machine with different number of cores to vertically scale to traffic load. Let's have a closer look on how data dependency vectors work. We run a middle box and a replica with 2 threads. Note that they could have different number of threads, but we use the same number of threads for simplicity. Middle box state is divided into 3 partitions. As shown, the data dependency vectors of the middle box and its replica contain 3 sequence numbers corresponding to these 3 state partitions. We assume that the middle box and replica initially have the same dependency vectors. 2 packets arrive to the middle box at approximately the same time. The first packet is processed by the first thread. To process this packet, the first middle box threads writes to the state partition 1. For this transaction, FTC only records the sequence numbers of the state partition 1, and for other partitions, it uses don't care value, denoted by X, showing that there is no need to track these partitions because the transaction did not access these partitions. FTC also increments the sequence number of state partition 1, showing that this partition was involved in a transaction with a state write. The second thread processes the other packet. The packet transaction reads state partition 1 and writes to the state partition 3. The transaction depends on the first transaction because it reads the write that the first transaction has performed on state partition 1. FTC records the sequence number of state partition 1 and 3 and uses don't care value for state partition 2. FTC also increments the sequence number of state partition 1 and 3, while the sequence number of state partition 2 remains unchanged. To ensure consistency, the replica must first replicate the state changes of the first packet before those of the second packet. However, the second packet arrives before the first one. The replica compares the data dependency vector of this packet with its local dependency vector. Because its local vector is smaller than received vector, the replica realizes that this packet has arrived out of order and does not apply its state changes. After a while, the first packet arrives to the replica. The replica compares its local vector with the received data dependency vector, and because its vector is greater than or equal to the received vector, the replica knows that the first packet is in order, and it applies its state changes. The replica also updates its local sequence numbers of the partition whose values are not don't care, which is state partition 1. After applying the changes of the first packet, now the second packet becomes in order, and the replica applies the changes and updates the corresponding sequence numbers. We evaluate FTC by comparing that with two other systems, an F, a non-fault tolerant system that provides ideal performance, and FTMB. FTMB uses state logging and snapshots to provide fault tolerance for middle boxes. We use two implementations of FTMB. The first implementation, labeled as FTMB, only performs state logging. The second implementation, labeled as FTMB plus a snapshot, performs both state logging and snapshots. We use two evaluation environments. Their details alongside with other experimental setup details are listed on the right side. We compare the throughput of the approaches for a NAT middle box. We vary the number of NAT threads and measure the NAT's throughput. As shown, FTC comes with low overhead compared to an F. FTC improves the throughput of FTMB by two factors. This improvement is because FTC does not track read-only transactions, while FTMB logs reads to provide fault tolerance. To evaluate the throughput of chains, we vary the chain length and measure the end-to-end throughput. As shown, FTC throughput is largely independent of the chain length. FTC throughput is twice the throughput of FTMB, and it achieves 3.5 times higher throughput compared to FTMB plus a snapshot. The throughput of FTMB plus a snapshot drops by almost 40% due to periodic snapshot taken at all middle boxes of the chain. Snapshots at each middle box result in stalls in consequent middle boxes. No packet is processed during a snapshot. The throughput is affected by more snapshots taken in longer chains. We compare the per packet latency of a chain of 3 middle boxes. The tail latency of FTC for individual packets is only moderately higher than the minimum latency. FTC incurs 16 to 20 microsecond per middle box latency, which is 30% less than the latency of FTMB. Providing fault tolerance for middle boxes and chains is increasingly becoming more important. Current approaches to middle box fault tolerance are highly inefficient for a chain of middle boxes. They are inefficient because they treat the middle boxes of a chain independently. FTC changes the perspective by treating the entire chain as a fault-tolerant unit. FTC uses in-chain replication to replicate the state of middle boxes across the chain. Using transactional packet processing, FTC greatly simplifies the development of fault-tolerant multi-core middle boxes. Using data dependency vectors, FTC enables concurrent state replication. By using these techniques, FTC improves the throughput of the state-of-the-art by 3.5 times.